In this section, we will continue looking at the derivative, but in the last section, we talked about the derivative of a function at a specific point, and we recognized that that was the slope of the tangent line to the function at that point. In this section, we will look at the derivative as a function itself. So rather than looking at a specific point, we'll say what is the function that is the derivative of a given function for all of the values of x in the domain of the derivative. That wasn't quite right. So for all the values of x at which the original function is differentiable, and we'll talk about how to determine where the original function is differentiable. So our objectives are define the derivative function of a given function, graph a derivative function from the graph of a given function, state the connection between derivatives and continuity, describe 3 conditions for when a function does not have a derivative, and explain the meaning of a higher order derivative, like a second derivative or a third derivative or a fourth derivative. So I kind of explained this first paragraph here already, so I'm going to jump down to this definition. The derivative function says this: let f be a function. The derivative of that function at a given point x is given by f prime of x equals limit as h goes to 0, and then we see that same difference quotient that we saw in the previous section, but instead of an a, which would have represented a specific point, we see x as the input. So h is still the increment for the difference quotient, and we're still letting h go to 0, but instead of focusing on a specific point, we're trying to develop a function that can take any input. So not really a new formula to memorize, just a new way of looking at that formula as a function itself rather than just a number as an output. So again, more terminology. We have differentiation is the process of finding a derivative of a function. A function is differentiable at a value of x if its derivative exists there, and is differentiable in an open interval from a to b if the derivative exists at each point in the interval. So f prime of x is probably the most common notation you'll see for the derivative of a function that has been named f, but you might also see, if y is the name of your output, you might see dy dx to also represent the derivative function, or y prime, or this d dx in front of a function. So you might see this, for example, as the derivative of, and then whatever is coming after it. In the next one, we'll be looking at the derivative of 3x squared minus 2x plus 1. So this d dx is almost what's called an operator, and it takes an input. So you'd say the derivative of, and then say what the derivative, say which function you're differentiating right after it. And then these others, df, dx, or the capital D with a subscript x, that's the differentiation operation. And then the subscript is telling you what the independent variable is, what the input is. And that notation is used more in physics, is my understanding. So example 1, we have f prime of x is, we're trying to find f prime of x if f of x is 3x squared minus 2x plus 1. And then we want to look at these graphs for f and the derivative. Right? So again, rather than finding the derivative at a specific point, we're just finding this function that represents the derivative at any input x. And so we set up the difference quotient, limit as h goes to 0, f of x plus h minus f of x over h. Same difference quotient as, I think it was formula 1 from the previous section. I could be wrong. That could be formula 2. I don't have their numbers memorized. But f of x plus h will look like 3 times the quantity x plus h squared minus 2 times the quantity x plus h plus 1. And then we want to subtract f of x. So we'll subtract 3x squared minus 2x plus 1. And again, anytime f of x has more than one term, you want to be sure to put parentheses around that group so that you subtract all of those terms. And then I want to expand the numerator, and I have my binomial squared, so that will look like x squared plus 2xh plus h squared. Now I'll distribute my -2, and I'll distribute the subtraction, or that factor of -1. And I still have divided by h. Then I distribute the 3. And I keep simplifying my numerator until my goal is to be left with a bunch of terms that have a factor of h in them so that we can reduce that factor of h in the denominator. We should be there in this next step. I have a 3x squared minus 3x squared. I have a 2x minus 2x, and I have a 1 minus 1. And the terms that are remaining are those 3, and they all have an h. So I want to factor an h out of those. And it's always good to double check that if I were to distribute this h, I would get back to the 3 terms that I had there. And I certainly would. I'd have 6xh plus 3h squared minus 2h. This seems to be a common step at which many errors are made for students. So take that moment to distribute that h and make sure that you would have the terms that were there on the previous line. And I lost my limit as h goes to 0 in front of this whole thing. And that's important. So I'm going to make sure that I put it back. Because I don't want to lose that until I actually am at the point of substituting that h. And here's where I can do that. Right now I have that h over h, which reduces to 1. And now if I do a direct substitution, I have 6x plus 0 minus 2. So I just get 6x minus 2. So the derivative for this function is another function, 6x minus 2. So that means at any x value, if I want to know the slope of the tangent line, I can plug that x value into this new function, the derivative function, and find the slope using that function. So what we're thinking here is the outputs for f prime of x give the slope of the tangent line to y equals f of x at the point x, f of x. So let's take a look at these two graphs and see that the y values from the graph of f prime seem to track the slope of the tangent line to the graph of f. Let's see, we want to take a look at these two. So I have 3x squared minus 2x plus 1 and 6x minus 2 showing up here. And I can see that when the graph of f, which is the parabolic function here, is decreasing and would have negative slopes for the tangent lines, the y values on the graph of f prime, which is the linear function here, are negative. Where the graph of f hits its low point and would have a horizontal tangent line, so a tangent line with slope 0 at this vertex here, the y-coordinate on that blue graph is 0. So the slope of the horizontal tangent line to the graph of f corresponds with the y-coordinate of 0 on the graph of f prime. And as the graph of f is starting to increase to the right of the vertex, the slopes of the tangent lines would be positive and getting steeper, and we see the y-coordinates on the blue graph getting larger and positive. So it seems like everything matches up the way we want it to. Example 2, we've got a radical function here, and we're just wanting to use the difference quotient to find the derivative. And now instead of writing f prime, we're writing dy dx. But same idea, we will have the limit as h goes to 0, f of x plus h minus f of x divided by h. So we'll have the limit as h goes to 0. F of x plus h will look like square root of x plus h plus 2. We're just substituting x plus h where the x is in our formula for the function. And then we'll subtract square root of x plus 2 and divide by h. And we see that this would be a situation where I want to multiply in the numerator and the denominator by the conjugate of the function, or excuse me, the conjugate of the numerator, because that's where the radical is. So leave the two radicals the same, but make a plus in between. And then we've got in the numerator, we have an a squared minus b squared pattern. And the denominator, we're just going to leave that factored because our goal is eventually to cancel that factor of h. So if we distribute it, we'll have to factor it out again later. So we might as well just leave it, even though it looks messy. And in the numerator, I'm going to have, like we said, that a squared minus b squared pattern. A squared will look like, not that, x plus h plus 2. We'll just take that square root off. And b squared will look like x plus 2. And then I'll need to subtract both of those terms. Again, I'm carrying my limit as h goes to 0 along. I have x minus x, and I have 2 minus 2, and there's still an h left there in the numerator. And now I'm at the spot where I can reduce this h over h and make a 1 in the numerator. And I'm also at the point now, once I've done that, where I can do a direct substitution, and I'll drop my limit as h goes to 0 because I'm actually substituting h equals 0. And I will have 1 over square root of x plus 0 plus 2 plus square root of x plus 2. And since those radicals are the same, I can say, well, now in the denominator I have 2 of that radical. And I can rewrite it as 1 over 2 times the square root of x plus 2. So to summarize, we determined that dy dx is 1 over 2 times the square root of x plus 2. Right? And so again, let's look at the graphs, and what we want to remember is the outputs, or the y-coordinates, of the derivative should track the slope of the tangent line to y equals square root of x plus 2. So grab your graphing calculator if you have one handy, and let's take a look at these two. So square root of x plus 2, we see here, that's just our radical function shifted to the left, 2, our square root function. And if you notice, right where the function quote unquote starts, right? So at negative 2, 0, the function is actually quite steep there. And the tangent lines all are going to have positive slope, but they are less steep as I move to the right. So what I should see on the graph of the derivative is y values that are large and positive as we're close to this point, negative 2, 0, and then y values that remain positive but become less right, closer to 0 as I move to the right, because this graph gets less steep as I move to the right. So you can see here that graph, I just added the derivative, the 1 over 2 times the square root of x plus 2, and the y values for x's that are really close to -2 are very large. And then as x increases, the y values on the derivative become closer to 0. Still positive because the function is increasing, so it has positive slope for its tangent lines, but the derivative values are closer to 0. Okay, so in example 3, we have two functions whose graphs are given, and we're just trying to use the graphs and not use formulas to figure out what the derivative function will look like. So what we want to be thinking is the derivative is tracking the slope of the tangent line at each point. And the left side of this is linear, and we can see the slope seems to be -1 because I would move down 1 and right 1 to get to the next point. So if I'm tracking the slopes with my y values, all of the y values on that stretch are going to be -1 because the slope is -1, -1, -1, -1 as I move along there. And on this side, to the right, this would be linear again, but now the slope is +1. So if I'm trying to create another function that tracks the slopes, I want those y values to be +1. And then we have this issue of right at this corner, what to do. And since the two sides are doing different things, right at that corner, we're going to have two open circles because there's an abrupt change in the slope right there. It's not a smooth transition from one to the other. We have up to that point to the left, slope -1, and after that point to the right, slope 1. And then right at that point, we will just have open circles indicating that the derivative there doesn't exist. So this derivative function will be a piecewise function. For values of x that are less than 2, we'll have the y value -1, and for y values of x greater than 2, we'll have the y value 1, and right at 2, the derivative will be undefined. The next one, we can see if I sketch in some tangent lines here, we have negative slope, still negative slope, but maybe not as steep. Still negative, but not as steep. And then right at the origin, we seem to have a horizontal tangent line. Which would mean slope 0. So I know I can mark a point there with just the y-coordinate 0. And we said in this stretch, we have negative slopes but less steep closer to the origin, or let's say closer to x equals 0. And then on the other side, again, we have negative slope. Whoops, that's not very tangent, but negative slope and negative slope. So here again, we have negative slopes. And similarly, they are less steep closer to x equals 0. So on both sides of x equals 0, we have negative slopes, so we want negative y values for the derivative. And the further we are from x equals 0, the steeper these lines are. So the larger in absolute value the y values will be, but they'll be so large negative y values. So our derivative graph might look something like this. And I'm not being incredibly accurate about what the exact y values are, but just what's the pattern, that we'll have something that looks like a parabola that's been reflected over the x-axis. Right? If the original function has negative slopes for its tangent lines, the derivative function has negative y values. Where the original function has a horizontal tangent line, the derivative function will have a y value of 0. So we'll have an x-intercept. So there we were able to just use the graphs to sketch an approximate sketch of the derivative without having a formula for the functions themselves. In example 4, we'll do the same kind of thing, but instead of being given a graph, we'll just develop our graph. So we're looking here at the greatest integer function, and again, sometimes we see that as int with an x as an input. Sometimes we see it with this like double bracket. And we want to think about what that graph looks like and then sketch the derivative. So you remember that this function takes an input and then rounds it down to the nearest integer that's less than or equal to this value. So 0 would stay at 0, 1 would stay at 1, but anything between 0 and 1, say a half or a third or a 3/4, is going to get rounded down to 0. And then we have an open circle on the end of that step. And similarly, anything between 1 and 2 will get rounded down to 1. But as soon as I get to 2, I will jump up to 2. So we have these steps. And we have the same pattern extending for negative x values. So our steps look like this. So in red, I have f of x equals the greatest integer function. And we want to think about what the derivative would look like. So I'll do that in light blue. So what we can see here is that these steps all have slope 0. Right? So we'll have slope 0. I shouldn't have filled that in. Anywhere that's like on the interior of a step. But if we think about trying to do a tangent line as we move from the left side of any one of these jump points, we're going to get values for the slopes that are very steep, right? The steeper and steeper, the closer we get to that jump point. So we'll have a discontinuity in the derivative function because the derivative right at one of these jump points will be undefined. So we'll have this function that's 0 everywhere except at the integers. Right, so where the derivative is defined, it will be 0. But anytime we hit one of those jumps, we will have an undefined derivative. So what we can see is there are several ways where a function can fail to be differentiable. One of them is discontinuity, as we see here with this step function. Another is a sharp corner or turn. Right, so not like a parabola and its vertex, but more like the absolute value function and its vertex. So we've got a sharp change in direction, not a smooth change in direction. And then another is a vertical tangent line. And that one we could see actually from our graph of this square root of x plus 2. The original function had domain all the way out to -2, but the derivative itself, notice the domain does not include negative 2 because that would give us a 0 in the denominator. So the domain for that is simply x is greater than negative 2. And what's going on right at negative 2 is what we would call a vertical tangent line. Not an asymptote, but a spot where the derivative, the tangent line itself is getting steeper and steeper and steeper and steeper to the point of being vertical as we approach negative 2. So those are the things we want to watch for when we're looking for failure of differentiability. There is or are other more complicated ways a function can fail to be differentiable, but we won't run into these very often. But one of them is like incredibly fast oscillation, like you would see with the function x sine of 1 over x for x not equal to 0, and then x equal, or for 0 if x equals 0. Let's just look at that graph really quickly. So if we add here, we wanted x times sine of 1 over x. Turn these others off. If we zoom in closer to 0, we see this function just oscillates so quickly that we can't talk about the derivative there because it's just changing too quickly. So that's another thing that can happen. So it's not necessarily a discontinuity, it's not a sharp corner or turn, there's not a vertical tangent line there, but it's still not differentiable at x equals 0. So mainly just be concerned with these three that we outlined. Watch for discontinuities, watch for sharp corners or turns, and watch for vertical tangent lines. So let's take a look here at example 5. We have just a graph that's given, and we want to figure out first the places where the function is discontinuous. So let's see, we could see definitely there's a discontinuity at x equals negative 1. And that's, just to review, that's a jump discontinuity because the two sides are not even approaching the same value. There's another discontinuity at x equals 0. One side it seems to be approaching infinity, and the other side is approaching 3. So it's hard to say. On one hand, it looks like an infinite discontinuity. On the other hand, it looks like a jump discontinuity. I think you could go either way. I'm going to call it infinite since one side is seemingly unbounded. And then x equals 1. That would be a removable discontinuity because all we would need to do is redefine that one value. And we would have continuity. Right? So we have f discontinuous at these 3 points. And remember, if it's discontinuous at those points, also differentiable. So, excuse me, also not differentiable. And then we also have places where the function is continuous but is not differentiable. And those would be places where we see a vertical tangent line or a sharp turn. So let's see, certainly like here at 2, we have a sharp turn. And that's, I guess, the only other thing I'm seeing on this graph. I don't see any place where it appears that there is a vertical tangent line. We mentioned already what appears to be a vertical asymptote at 0, but that was a discontinuity. So I think we've covered everything. So we've got the places where f is just plain discontinuous, and then this one spot at 2 where the function is continuous but is not differentiable because of that sharp turn. Then in example 6, we have a piecewise function with two parameters, a and b, that we can play around with. And we want to figure out how to make this function both continuous and differentiable at 3. So let's take a look at what this function is doing using GeoGebra. So we can imagine, I'm just going to make a quick sketch before we grab GeoGebra to get a start at visualizing this. One of the two branches, x squared, is not changing. It's not dependent on a and b. So we have, let's see, 3, and it would be, what, 3, 9? And then it's the parabola going up from there. So that branch is fixed. We know exactly what that looks like. Right? The other branch is linear, and its slope is whatever our a value is, and its y-intercept is whatever our b value is. Right? So we can change the slope by adjusting a, and we can change the y-intercept by adjusting b. And we want to make sure that this function is continuous and differentiable at 3. Right? So continuous would just mean roughly that the graph is connected. Differentiable is telling us there's a smooth transition between the two branches. So let's grab GeoGebra, and let's get rid of that one and put these in. Okay. So I typed these as x squared, comma, x greater than or equal to 3, and GeoGebra turned it into this if-then statement. And the second I typed as ax plus b, comma, x less than 3, and GeoGebra automatically built in a slider for me for a and b, and also turned it into that if-then statement. Okay, so what we're going to do is first adjust so we can see these. So right now it looks like my a value, the slope, is at 2.8, and my b value is at 4.1. I'm going to slide these back so they're both at 0, and then just play around with them a little bit. Okay, so if they're both at 0, clearly I just have this horizontal line, and that's not going to work. And I can think, well, I could just shift that up. Whoops, my limit is set not high enough there. Change the settings so that I can go up a little bit higher. And I could shift that up, and I could say, well, there, now I have something that's continuous, but it's not differentiable, because that is definitely not a smooth transition between those two. So I can see, well, if I want differentiability, I need to play around with a, that slope. Well, that's making it even worse if I make a negative. So maybe I want to make a positive. And it looks like, well, maybe I make a positive, but now I need to just slide this back down a little bit so that they meet up. I can say, well, that looks better, but it's still not quite a smooth transition out. So maybe I need something a little bit steeper. And then I'll move my B down, and I can just kind of play around with this. Looks like I might need it even a little bit steeper still. And then I would need to move my B limit down. And it's getting closer, right? So I can see how A and B are impacting things, and I can kind of get this sense of what I'm trying to achieve. I want continuous, and that's going to involve getting the right y-intercept so that those two connect. And then I want this to be a smooth transition, and that's going to depend on the slope. So let me try to get rid of this GeoGebra. For connected, I need the two branches to match. So that's going to involve the function values being the same. For the two branches. And for a smooth transition, I need the derivatives agree for the two branches, right? So for the right side, my function value at 3 would be 9, and I need to figure out what the derivative is. So I need to track what's the derivative of x squared. So I want the limit as h goes to 0, f of x plus h minus f of x divided by h. So I'll have the limit as h goes to 0, x plus h squared minus x squared over h. So limit as h goes to 0, x squared plus 2xh plus h squared minus x squared all over h. And I can now factor an h out of the two terms that are remaining after I do x squared minus x squared. And that's going to give me h times 2x plus h. And I can reduce my h over h, and then I'm allowed to do a direct substitution, and I will just have 2x. So the derivative for the right side would be 2x, and I also need to know the derivative for the left side. So my notation, again, remember, means the derivative of and then whatever I put inside. So the derivative of ax plus b, and that's just a line, and we know that the derivative for a line is just its slope. I'm not going to go through all the work for that. You could go through it, but I'm comfortable with you recognizing that the derivative for something that's linear is just the slope. So the derivative for that will just be a. So the function value we need to agree, and also the derivatives we need to agree. And we said for the right side, the function value is going to be 9. So we need a times 3 plus b to be 9 to get the function values to be the same. And for the derivatives to agree, we need the derivative at the right, which would be 2 times 3, to be the same as the derivative on the left side, which would just be a times 3. Excuse me, just a, because the derivative is a, not a times x, right? So we can see, well, okay, that tells me exactly what a is. It tells me a is going to be 6. And then if I use that a equals 6, and I plug that in over here, I have 6 times 3 plus b is 9. That is going to tell me b is 9 minus 18, so negative 9. So our solution seems to be use a equals 6 and b equals negative 9. So we end up with 6x minus 9 if x is less than 3, and x squared was given if x is greater than or equal to 3. So let's take a look at GeoGebra and make sure that looks like it is accurate. So 6x minus 9, we said. So it looks like a is supposed to be 6, and b is supposed to be negative 9. Looks pretty good. It looks like those graphs definitely match up, and it looks like there's a smooth transition at that point where x is 3. Right. Great. And now I've lost my notes. Let's see here. The last Okay, so then we have a theorem that says differentiability implies continuity. And so it just says if f is differentiable at c, then f has to also be continuous at c. We can't have differentiability without continuity, right? Because if the function is discontinuous, then we know the function is also not differentiable. But the other direction for the implication is not true. We cannot say if f is continuous, then f is differentiable, right? And this is a true-false question asking us to think about that. It says, is it true? If f is continuous at a point, then f is differentiable at a point, at that same point. And take a minute for yourself and see if you can think of a function that we've already run into that would be a counterexample here. So this is false. So you're trying to think of, is there a function that you can think of that is continuous at a point that's not differentiable at that same point? And for me, the easy one to think about is like an absolute value function. That function is continuous at 0, but not differentiable at 0. So we could say false. Consider f of x equals absolute value of x. Continuous at x equals 0, but not differentiable there. So something with a sharp corner is an easier thing to think about. Another example could be like the function cube root of x. That one's just not quite as obvious, but cube root of x has a vertical tangent line at x equals 0. It's just steeper and steeper and steeper the closer we get to 0. So that function is continuous at 0, but not differentiable because of that vertical tangent line. But absolute value of x is the easiest one to use, I think, as a counterexample. All right, so then the last thing to look at is what are called higher order derivatives. So first derivatives we've talked about already, second derivatives, third derivatives, fourth derivatives, nth derivatives, right? And we've already mentioned this, that the derivative of a function is itself a function. And so if we have another function, we can talk about another derivative, right? So a second derivative would be the derivative of the derivative. A third derivative would be the derivative of the derivative of the derivative, and so on. There's a physical example that we run into frequently, which would say the position function, if that's our original function, the velocity is its derivative, and acceleration is the second derivative of position, or the first derivative of velocity. Right? So the notation we're going to run into for higher order derivatives will be this. You'll notice we can use tick marks to indicate which derivative we're on. But once we get past the third derivative, it's common, instead of using tick marks over and over and over, it just get to be a lot of tick marks, we'll switch to the number of the derivative in parentheses. And the parentheses help distinguish it from this, which would be y multiplied by itself 4 times, right? So switch to a number once you get past the third, and then put that number in parentheses so that you know it's the derivative, not the power of that function. So you can see how we transition between the first derivative, the second derivative, and the third in each of these notations. The y prime or the f prime, it's pretty straightforward. The dy dx notation, notice that you have the exponent on the d in the numerator to say I'm doing this derivative this many times, and you have it on the x in the denominator. This will be more interesting to us when we get into multivariable calculus and multivariable functions, because we might have maybe z as a function of x and y, and maybe we first take the derivative with respect to x and then take it with respect to y 2 times or something like that. So the denominator tells you which variable you're using for the independent variable each time. So again, this notation seems a little bit strange when we're just in functions of a single variable, but this function gets much more useful to us when we're looking at functions of several variables. So let's take a look at this next example. The position of a particle moving along a straight line is given by this s of t. Our input is in seconds and our output is in feet. And we want first the function that gives the particle's velocity. And so that would be the first derivative of position, and we'll call it v of t. And the particle's acceleration, which is the second derivative of position and the first derivative of velocity. So we'll say v of t, the first thing we want to find is the derivative of the position. And we'll go back to our difference quotient limit as h goes to 0. And now instead of f of x, we have s of t plus h minus s of t divided by h. And that's going to look like the limit as h goes to 0. 5 times the quantity t plus h squared minus 3 times the quantity t plus h plus 2. Excuse me, and then we want to subtract 5t squared minus 3t plus 2, all of those terms, and we want to divide by h. So hopefully you're getting used to simplifying these. We want to expand the numerator, but first we'll expand this binomial. So we'll keep the 5 out, t squared plus 2th plus h squared, distribute by negative 3, and then distribute the subtraction, which is distributing a factor of negative 1. And lastly, distribute the 5, and then we can start adding and subtracting terms. So we have 5t squared minus 5t squared. We have 3t minus 3t, and we have 2 minus 2. And we're left with, let's see, something not right. I have a 10t that should have an h with it there. So I know that everything that's left should have an h, so I needed to double check. When I distributed my 5, I lost that factor of h, but now we've got it back. There we go. So 10th plus 5h squared minus 3h, and those all have a factor of h, so I'll factor that out. And then I'll reduce my h over h, and then I'm at a spot where I can do a direct substitution. And so I have 10t plus 0 minus 3, or simply 10t minus 3. So I find that my velocity function is 10t minus 3, and that would be feet per second, since our output for the original was feet and the input was seconds. And the last thing we're asked to do is find the acceleration, which is the derivative of v, which is also the second derivative of s. Right. So using the derivative of v, now I want the limit as t goes to 0, v of t plus h minus v of t, all divided by h. So same derivative pattern, but now my starting function is v. And so now I've got limit as t goes to 0. V of t plus h is 10 t plus h minus 3. And subtract v of t, so 10t minus 3, both of those terms are subtracted. And then divide by h. Limit as, I am seeing another mistake. This should not be t going to 0, I should let h go to 0. Limit as h goes to 0. Let's distribute the 10t plus 10h minus 3 minus 10t plus 3. And I can see I have several things that will add and subtract to make 0. And what I'm left with is 10h over h. And that reduces to 10. So now I have limit as h goes to 0 of 10, which is simply 10. And again, right at this point where we saw v of t is 10t minus 3, we could say that's linear. Its derivative is just going to be its slope, which is 10. That would be fine, but here's how you would go through that the long way. And let's talk about the label. So v of t was feet per second, so we'll have feet per second, because it's the label from the output, which was v of t, divided by the label for the input, which was t. And typically, instead of writing feet per second that way, we would write 10 feet per second squared. But it's easier to see in the first version where this second squared is coming from. Feet per second per second. All right, in the next section, we will start to look at faster ways of finding the derivative, but it's important to understand that it's all tying back to this difference quotient.